Ionic bonds. When a metal bonds with a non-metal and the electron is transferred from the metal to the non-metal, we call that an ionic bond. So recall from a previous video, if you need to go back and look, that we defined a metal as an atom with a low effective nuclear charge, one that does not have a good hold on its own electrons. There's not much attraction between the nucleus of that atom and its electrons. Alternatively, a nonmetal is defined as an atom that has a high effective nuclear charge and therefore a high attraction for the electrons. So, why does it happen? Well, let's take an example compound of magnesium fluoride and work through it. So magnesium, Mg1224, has 12 protons, 12 neutrons. Not that it matters that much, but whatever. There's 2 electrons on the first shell, 8 electrons in the next shell. And if we're going to assume we're starting with neutral magnesium, it isn't any sort of ion yet, we will add another shell with 2 more electrons. Now, from a chemical reactivity standpoint, if we want to consider this, we should consider what it's going to look like just to the valence electron, so we should find the effective nuclear charge. Here we have 12 protons and 10 inner electrons, leaving us with an effective nuclear charge of +2. So when bonding, this atom effectively looks like a +2 with 2 electrons around it. So that's magnesium. Fluoride. Fluoride is 9 and 19. Fluoride has 9 protons, 10 neutrons, 2 electrons in the first shell, 7 electrons in the next shell. And again, if we want to simplify this for bonding, we can recognize that this all appears like one object with an effective nuclear charge of the number of protons, 9 minus the inner electrons, 2, which is +7. So +7 with its 7 valence electrons around the outside. So there we go. We have our nonmetal, high effective nuclear charge of +7, and our metal, low effective nuclear charge of +2. Keep in mind here one more time, the range is from +1 to +8. So +2 is on the low end and +7 is on the high end. What that means then is that this +7 is so strong that what it can do is it can actually rip one of these electrons away. It can't rip 2 away because it doesn't have space for 2. But what can happen is another fluorine atom can come along with its 7 valence electrons and rip the other guy away. And what's going to end up happening here then is that this magnesium atom, having lost 2 of his electrons, will be left as 2+. And these 2 fluorine atoms, having taken on extra electrons, will now have 8 valence electrons around them. And its overall charge will be -1. And to make this molecule work, it would have to have 2 of them. One to take one of the electrons, the other one to take the other electron. This is also important because we can see that the overall resulting thing here is neutral. We have 2+ magnesium plus 2 1 minuses from the fluorines, which leaves us with 0, or a neutral grouping. What really happens here is this forms into a giant crystal, repeating over and over again. And the simplest part of that crystal is called a formula unit. So that's the simplest part of a ionic crystal formula unit. Now, that assumes that fluorine is strong enough to rip these electrons all the way from magnesium, so the electron is transferred. That's what makes this an ionic bond. And that's why it typically takes a metal and a non-metal. It takes somebody who's willing to lose the electron, and it takes somebody who's willing to or interested in gaining the electron. Now, with all that in mind, how do we know if the attraction for something like fluorine is strong enough? And to do that, we use something called the electronegativity difference. That is the electronegativity of the non-metal minus the electronegativity of the metal. So taking something like fluorine and magnesium, my electronegativity difference for fluorine, just looking up on a chart here, it has an electronegativity of 3.98. And for magnesium, it has an electronegativity difference of, electronegativity of 1.31. So if I take the difference here, I get an electronegativity difference of 2.67. That basically says how much more fluorine wants that electron than magnesium does. The benchmark that we use is that if the electronegativity difference is greater than 1.7, we say the electron is transferred, and we call it an ionic bond. If it's less than 1.7, the electron is shared, and we call it a covalent bond. More on those later, but clearly we can see saying it's a metal and non-metal isn't enough. There's an actual quantitative way of figuring that out. So let's do this for calcium oxide and beryllium nitride, and we'll see. So a short form for electronegativity difference is sometimes we use the delta, which means difference. So we can write electronegativity difference like that with the delta and the En. And then if I look up calcium oxide, oxygen is my non-metal, and its electronegativity is 3.44. You can't see it here, but I have a periodic table I'm sneaking peeks at. And calcium is 1.00. Oh, that's an easy one. So my electronegativity difference here is 2.44. 2.44 is bigger than 1.7, or if you want to use the greater than symbol. So we say that this bond is ionic. So in this case, this is calcium oxide. In this case, we would say that this is forming a proper ionic bond, which means that calcium is giving its electrons to oxygen. This is as predicted with a metal and non-metal, right? This one was the metal, this one was the non-metal. But let's look at another combination here of a metal and a non-metal. Beryllium nitride. The electronegativity difference here for beryllium nitride, nitrogen is 3.04. Nitrogen, or beryllium, is 1.57. So the difference here, so it would be 4, is 1.47. So that is not quite big enough. 1.47 is less than 1.7, or less than if you want. This is then, even though it is a metal and a non-metal, it does not pass our test to say that the electron will be transferred. The difference isn't big enough. So this is actually a covalent bond, which means that if these guys met in nature, nitrogen wouldn't be strong enough to rip the electron away from beryllium, and so these two things would actually form a covalent compound instead of the expected ionic compound. It's a little bit of a spectrum. It's not to say that this covalent compound wouldn't look a lot like an ionic compound, but there is a quantitative test and it doesn't quite meet the expectation. So that's what an ionic bond is, and that's how you tell if the difference in the attractiveness of the nuclei is strong enough to cause it to be ionic, as in to cause the electron to be transferred, or if it's not strong enough and as a result it'll be shared.